So continuing from the previous video clip, so this will be 1 minus 1, that is 0, and then b dot c, so b is 1 minus 1 minus 1, and then c, that is 1 0 1. So it is 1 into 1 minus 1 into 0 minus 1 into 1, so it is also 0. So in this case we can say that S is an orthogonal set. This is an orthogonal set. As a second case, we check another set. We check whether it is orthogonal or not. So S is equal to this set 1 minus 1 2 0 2 and 1 minus 1 0. So we can call them as sets A, B and C, vectors A, B and C. So A dot B will be 1 1 minus 1, dot B will be 2 0 2. So it will be 1 into 2 plus 1 into 0, 1 dot 1 into 0, into 0 plus, that is minus 1 into 2. So 1 into 2 minus 1 into 2 and then 0, that is this 0. A dot B is 0. A dot C 1 1 minus 1, so 2 0 2. So it is 1 into 2 plus 1 into 0 minus 1 into 2. So it is not 2 0 2, it is 1 minus 1 0. 1 minus 1 0, and then 1 into 1 plus 1 into minus 1 minus 1 into 0. Okay, so 1 into 1, so 1 minus 1 0, and that is 0, so this is 0. Okay, and how about B dot C? 2 0 2 dot 1 minus 1 0, so it is 2 into 1 plus 0 into minus 1 plus 2 into 0. So this is 0 0, but this is 2, this is 2. So in this case, since B dot C is not equal to 0, so set S is not an orthogonal set. Okay, set S is not an orthogonal set. So A dot B and B dot C that means if any of the combinations is not equal to 0, then we will say that the whole set is not an orthogonal set. Although A and B are orthogonal, but A, B and C together are not orthogonal. Okay, so next example is so if we have a set S which is a span of the two sets, which is the span of two vectors, so 3 3 0 and 4 2 minus 1. Okay, so that means by the span what we mean is that we can have any linear combination of these two sets, and then that will be the full set. And if we have a set U, and if we have a set U which is equal to 1 minus 1 into then what we want to determine is that if U is in the orthogonal subspace S. So if U is in the subspace S perpendicular, okay, S perpendicular. So which is the symbol for orthogonal complement, orthogonal complement. So in simple words, it means that this is this vector U is perpendicular or orthogonal to each of these two vectors. So we need to check whether if, for example, if we said this, that this is set A and this is set B, we need to check if A dot U is equal to 0 and B dot U is equal to 0. So this we need to check. So if it is 0, then we can say that U is the orthogonal complement S perpendicular symbol of the given subspace. So A dot U, so what is A dot U? 3, 3, 0 dot 1 minus 1, 2. So it will be 3 times 1 plus 3 times minus 1 plus 0 times 2. So as you can see, it is 0. So B dot U, it will be 4, 2 minus 1 and then dot 1 minus 1, 2. So it will be 4 times 1 plus 2 times minus 1 minus 1 times 2. So it is 4 minus 2 minus 2, so it is also 0. So it means that U is orthogonal to both vectors. So we can say that U is in, so we can say that, so it's confirmed that U is in S, this perpendicular, or U is the orthogonal complement of the given subspace. Okay, next example is question is we need to find a basis for S perpendicular for the subspaces, subspace S. And what is the subspace S? Subspace S is a span of uh, 1, 0, minus 1, 2 and 2, 3, 1, 0, 2, 3, 1, 0. Okay, so we need, if we are to find the S perpendicular, so it means that that will be, if for example that vector will be U. Okay, so in that case, that A dot U will be 0 and B dot U will be 0. If this is vector A and this is vector B, so A dot U will be 0, A dot B will be 0. So this whole system will make this equation AU will be equal to 0. Okay, so AU will be equal to 0. So in this case, then we can write an augmented matrix. So in this case, because the dot product is in effect the transpose of the vector times the other vector. So this vector A will be then transpose of these vectors. Okay, so columns will become row 1 0 minus 1 2 2 3 1 0, and then for the augmented matrix we will have 0 0 over here. So we can make the row operation 0, that will be 0, what will be that? This will be 3, and then which was because we multiplied by minus 2, so it will be 2 plus 1 is 3, and then minus 4, this will be minus 4, and then that is 0. So we get these two equations. So from the second equation, so if we take the components as u1 u2 u3, so it will be 3 u2 plus 3 u3 minus 4 u4 is equal to 0. So we need to take u3 is equal to s1, u4 is equal to s2, okay, as the free parameters. So in this case now 3 u2 will be equal to minus 3 s1, and then plus 4 s2, okay, minus 3 s1 plus 4 s2, or u2 will be equal to minus s1 plus 4 by 3 s2. And then from the first equation, u1 minus u3 plus 2 u4 is equal to 0. So u1 will be equal to minus, so u3 was s1, so u1 is equal to s1, and then minus 2 s2. So the vector u will be then equal to s1 minus 2 s2, and then minus s1 plus 4 third of s2, and then s1 s2. Okay, so we can write it into these two components, s1 times, that will be 1 minus 1 1 1, 1 minus 1 1, and 0, because this was s2, and plus s2, that will be equal to minus 2 4 third 0 1, okay, minus 2 4 third 0 1. So now we will say that these two components will be the will be the basis of, so what will be the basis of for s prime, okay. So the basis for s will be prime will be these two components, okay. So the set is 1 minus 1 1 0, minus 2 4 third 0 1. So this will be the basis for the s perpendicular, that is the orthogonal complement. Okay. That means these two vectors will form the basis for the orthogonal component. So any combination of that will be the orthogonal component for the given span, okay, for the given span of this. Okay. So this is the answer. So we can verify it. So for example, we can take the arbitrary values s1 and s2 as 1 and 1. So therefore the u will, if so, for example, like a verification. Okay, we will continue it in the next video clip.